So really, without further ado, I can introduce our speaker tonight is Professor Alan Fitzsimmons. I think we all know Alan mostly. He's a professor of astronomy at the Astrophysics Research Centre in Queen's University. He's going to talk to us tonight about what makes a great comet. And Alan has been observing comets for a long time, since he saw his first comet on the way to the pub in 1983. And I'm going to...
didn't go to sleep in the car.
Except for Alan, I'd like Alan to unmute yourself. And guys, can we all turn cameras off just so the focus is on Alan during his presentation? You can put any questions you have into chat and we'll handle those at the end. And I'll hand the floor over to you, Alan. Do you want to share your desktop? You should be able to.
Yes, thank you, Paul. And can you just confirm that you can see that slide?
Looks great, Alan, yeah.
Super, thank you. Yeah, so of course it looks great because this isn't one of my photos. Well, listen, I'll get started. I'd like to thank you all online in a virtual way for coming along this evening to hear me talk. Some of you may have heard me talk before, in which case my apologies, but clearly there's nothing on apart from Coronation Street this evening. I'd also like to explain the circumstances about why I picked this talk. It's a fact that, as Paul mentioned in his nice introduction, that I have been observing comets one way or the other since the early 1980s. And I've even managed to make part of a living out of it as an astrophysicist. But when people ask me why people do astrophysics, and more importantly, why does the government and the taxpayers fund astrophysics, I can come up with two answers. One of which is that it's a tremendous challenge to explore our universe and to understand our universe. And by doing so, I think we advance humanity and we advance our society as a whole. The second answer, which everybody is generally much more happy with, is that it makes great pictures for calendars. And because of that, that's why I chose this topic this evening, simply because I thought, let's not do too much science. We will be doing some, I warn you. But I thought, let's go back and take a look over some of the most spectacular objects that have appeared in the night sky, and use that as an excuse to see some wonderful images. So the title of my talk is really a question: what makes a comet great? Oops, no, I need to get onto here. Let's cut to the chase first of all. All comets are great. That's my opinion, and if you don't like it, tough, you're muted and I'm not. But seriously, folks, comets are wonderful objects, and part of their wonderfulness, I guess you would say, is simply that they do look spectacular. Every comet is different. Every comet behaves differently. The very famous pro-am astronomer David Levy in America once came out with a tremendous quote that is attributed to him, at least, which is that comets are like cats. They have tails and they do what they want to do. And so you're never quite sure what you're going to get with any comet. Particularly, of course, when a new comet is discovered, you're never quite sure, is this going to be a bright one? Are we going to be, are we going to have a tremendous spectacle in the night sky? And in this talk, I'm going to at least try to explain some of the factors that dictate whether or not we get a bright comet or even a great comet in the sky. So let's have 2 or 3 slides just to remind ourselves what a comet is. Comets are objects that orbit the sun, just as the planets do and the asteroids as well. But unlike the planets and the majority of the asteroids, the comets generally orbit in very elliptical orbits. Now, all orbits are elliptical, even the Earth's, that we don't have any purely circular orbits in the solar system. They're all slightly, at least slightly distorted from being circular. But when we look at comets, generally what we observe are, by and large, very eccentric or elliptical orbits indeed. And in this graphic, you can just see the orbits of the outermost gas giant and ice giant planets, Jupiter, Saturn, Uranus, and Neptune in blue, along with Pluto, one of our largest dwarf planets, and which tells you how old this slide is. And then in lighter blue or cyan, you can see the orbits of 3 comets, Comet Borrelli, or right there in the center, which kind of really stays almost within the orbit of Jupiter. And that's what we call a Jupiter family comet, or a short period comet. And then with larger orbits, and the larger an orbit is, the longer it takes to go once around the sun, we have, for an example, the orbit of Comet Halley on the left, and Comet Ikeya-Zhang going down towards the right. And these are, well, some people would call them long period comet orbits. We actually generally in the community call them Halley type comets after Comet Halley. They have orbital periods between a few decades, 20 years, and 200, 300 years or so, of which, of course, Halley is the archetype member. And as you can see in these orbits, they travel from the faraway cold outskirts of the solar system in towards the sun. Now, when a comet gets close to the sun, it has a tremendous effect on its surface. Of course, the closer you are to the sun, the warmer an object is. And comets themselves are made of comets come near the sun, and when they do so, they, because they have a large amount of ice in them, primarily water ice, the comet is warmed above what we call the sublimation temperature. Now, this is not an evaporation process, because evaporation is the term given to liquid when it turns into a gas. This is a process by which the solid ice immediately becomes a gas, and it has to do that because initially it's in a vacuum, of course, but even when there are these gas molecules around, it's still very close to a vacuum. The gas pressures are incredibly low. So as you can see in this image taken by the Rosetta spacecraft of Comet 67P, one can see clearly the gas being driven off the surface of the comet by just the warming of those ices, and entrained in that flow of gas will be these small solid particles that we call comet dust. Generally, they're microscopic, about 1/1000th of a millimeter or so across in images like this, but they span a range of sizes up to centimeter size, or even down below 1/1000th of a millimeter, all the way down to perhaps 1/1000th of a millimeter, just a few tens of atoms across.
Alan, the slides still aren't advancing. We're still stuck in orbits.
Really? You're not seeing any change there?
No.
Thank you. You can't. Which slide are you seeing now?
That's what is a comet, the nucleus, Alan?
Okay, thank you. Listen, folks, we'll give it another go. I honestly don't understand what the problem is. It may be a Zoom thing somewhere, not your side or not my side. I'm trying to shut down processes as well to make sure it's not my side. Let me just do this. Let me do that. Let me do that. So you can see that picture of the comet nucleus. Can you see this picture of another comet?
Yeah.
Tails, yes.
Comet West. Thank you. Thank you. Okay. If I just, it could be that it could have been my side, and I was just had too many processes open. I'm closing down everything apart from my slideshow, including my email. Okay. Let's see if this works. Apologies again, everybody. Anyway, if you can try to put together what we've been saying disjointedly over the past 5 or 10 minutes, the material released from the nucleus of a comet does not return. Mostly, some small fraction of it would, but the vast majority of it escapes into interplanetary space. And the dust and the gas, first of all, form what we call a transient atmosphere around the nucleus called a coma. Now, the coma of a comet is very different to the atmosphere of a planet. When we look at a planet like the Earth, most of the Earth is the planet, and the atmosphere is a very thin veneer around the surface of the planet. With a comet, that's completely reversed. The nucleus, probably only a few kilometers across, is in the heart of the comet, where the majority of the material is. But the material it releases to form the coma of the nucleus expands freely out until it's much larger than the actual nucleus. And as I've indicated here, a well-developed comet will have a coma of at least 100,000 kilometers across. And in fact, we can trace molecules from a nucleus easily out to 1 million kilometers from that very small nucleus in the center. And then the gas and the dust particles that's been released by the nucleus are pushed back from the sun by two different physical mechanisms. First of all, the gas is ionized by solar ultraviolet radiation, ultraviolet light from the sun. And when it becomes ionized, it becomes charged by having an electron knocked off them. Then that gas is dragged back, literally dragged away from the comet by the magnetic field in the solar wind. Now, we can see that ion tail in pictures like this because although most of those ions or those charged molecules are water molecules, perhaps 5 or 10% of them are charged carbon monoxide gas or carbon monoxide molecules. And whereas water doesn't reflect light very well at visible wavelengths, ionized or charged carbon monoxide reflects light in the blue region of the spectrum. And so whenever you get a picture of a comet like this and you see a blue wispy tail, that's your tail of ionized or charged carbon monoxide. And there'll be other ions in there, as I said, such as water and so on, but they just don't reflect the light very well. So we are dominated by what we see via the carbon monoxide molecules. The dust particles that form their own tail, and they are blown back simply by the pressure of sunlight on them. These dust particles, remember, are thousands of a millimeter typically in images like this. And over days and weeks, they are simply pushed back away from the comet by the pressure of sunlight itself. And so the actual act of the sunlight reflecting from those dust particles so we can see them also forms the tail that we can see. There's a lovely kind of symmetry there. Now, I don't want to give you the impression that all comets look like this. Okay, I might have given that impression up to now. If so, I apologize, because it was a false impression. I'm switching to the next slide, and it would be lovely if somebody could tell me that they can see this slide.
Yes, that's done.
Yes.
Thank you. Thank you. Actually, what I'll try to do is I'll try to put up the chat again. Oh, it's disappeared. Oh, can I see? I can't see the chat, I'm afraid, now on my screen, but you can see the slides, so I've got to leave it. Please shout out if you don't see the slides anymore. So here's a bunch of comets I grabbed a little while ago, as seen by the Pan-STARRS telescope in Hawaii. All of them look incredibly unimpressive. And that's because for the majority of their orbits, comets are not emitting any material, or they're only emitting small amounts. And the brightness of a comet, to first order, depends on how much stuff there is to reflect sunlight. And so if you're not ejecting any of this material from the surface of the nucleus, all you've got is the nucleus there yourself, and you're dealing with an object just a few kilometers across, way out there in the solar system. And if that wasn't bad enough, generally the reflectivity of comets, what we call the albedo, is about 4%. So the comets are only reflecting 4% of the light that hits it, which is actually darker than a piece of coal. So by and large, from much of their orbits around the sun, comets are not impressive beasts. But luckily, when they are near the sun, they can be. And we've just had a really nice example of that, of course. This summer, in July, we had Comet NEOWISE that was found earlier this year by the NEOWISE infrared survey satellite. And I've got a couple of pictures, a very lovely image here on the left, sent to me by Martin McKenna, show when the comet was near its brightest in the pre-dawn sky as seen from Northern Ireland. And then on the right, unfortunately, a much less impressive image taken by myself overlooking Antrim a couple of weeks, I think 2 or 3 weeks later. Although I think with that image, I like it because if you look very carefully to the upper left of that image, you can see the plough. So one can see the kind of scale that we have here. Now, relatively bright comets like this do come around fairly often, every few years or so. And they're lovely to look at, particularly in binoculars, of course. I'm sure that all the experienced observers here in the IAA full well know. But occasionally, about on average, once every 10 years, maybe once every 15 years, we get a truly spectacular comet. And right now, you're seeing me, and you're actually seeing kind of what I don't see. You're seeing the back of my study behind me. This is a picture of my desk that I'm sitting at the moment. I took about an hour ago. And if you look carefully, then just above my laptop, one can see a picture, which is actually an etching that was published on the June the 9th, 1843 in London. And that is a graphic showing some lovely ladies. Unfortunately, you can't see it too clearly, but it's some lovely ladies in the south of France, in Nice, admiring the Great Comet of 1843. And one may always assume that everything is available on the internet. I did a search for that picture for about an hour today on the internet. I could not find it. So here's another one. The Great Comet of 1843 was truly spectacular. A tail stretching like a searchlight, tens of degrees across the sky, and so bright that even when the head of the comet had set, the tail was still visible. And truly, an object like this in the sky back then, when they had very little problems of light pollution, would have been tremendously spectacular. But even today, if we had a comet like that appear in our skies, people would be able to see it. And in fact, the appearance of these bright comets or great comets in the skies have influenced us, influenced in terms of our society over centuries. So here's a couple of examples, for example. On the left, we have a picture by the great Renaissance medieval artist Giotto di Bondone. I'm not sure if I pronounced that right. Somebody can tell me in the Q&A afterwards. This is the Adoration of the Magi, worshipping the newly born Christ. And if one looks above the stable and the crib, one can see the Star of Bethlehem, except Giotto has painted it as a comet because of a comet that he himself had witnessed a few years earlier. On the right, we have a diagram showing the different types of comet one could see in medieval times, and it being a rather fractious period of human history with many wars. Generally, it was supposed that these were omens or signs of great battles and pretty awful events. And so, as you can see in this woodcutting here, the comets are drawn as daggers and swords. And that iconography remains with us today. You may not realize it, but we are even today surrounded by this impression we've gathered as a society, as a civilization, of these things appearing in the skies. A few years ago, I decided to walk around and take a look at pictures I could find of comets. Here's one. Here's a supermarket in the United States that I took a picture of when I was there. And yeah, here we have the Kiyomiku supermarket, whose sign is clearly a comet. If one goes into that supermarket, one could buy a bottle of bubbly to celebrate whatever one wanted. And look, there's a comet. Don't drink too much of that stuff, let's be honest, because particularly during these lockdown days, one may feel worse the wear the next morning, in which case you'll need some cleaning powder to remove the evidence. And oh, I challenge you, next time you're in Tesco's or Sainsbury's or even Lidl or Aldi, to have a look at the numbers of symbols of comets you might find there. Even in things like curtain fabric, one can see, and cloth, one can see images that clearly are inspired by the sight of comets in our night sky. And it's even stronger if one flicks between one of these graphics and a picture such as this, a wood cutting of the Great Comet of 1858, Comet Donati. So we've been influenced by these great comets over the centuries. There's no doubt about it. But I've been avoiding doing one thing up to now, which is defining a great comet. And there is no scientific definition. This is purely subjective. There are generally people agree, however, that if you're going to have a great comet, what does that mean? It means that it's a comet that's at least as bright as the brightest stars in the sky. So we're talking first magnitude or 0th magnitude. And if you want to have a comet that's truly memorable, you want a comet with a visually long tail, visually meaning not something you can spend an hour integrating with your modern digital camera to detect, but something you can see by eye in a reasonably dark site. And you want to see that. So you want to see it in a twilight or a dark sky, because there have been daylight comets, and we'll see an example of one later. But Generally, you have to know where to look. Certainly, however, the brightest comets can be seen sometimes if they're close to the sun in the daylight sky, but generally they'll be noticeable, of course, in a twilight or dark sky. And if we look over the past 100 years or even 110 years, because I wanted to, here's a list of generally what people would agree are the great comets over the past century or so. There's been a few, and as you can see, there's been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 or 11 of them in roughly the past 100, 110 years. So it tells us that on average, there's about one per decade. Now, you may not be able to see them because, for example, Comet Lovejoy, the last great comet to appear in our skies, was really purely a southern hemisphere object. It was not visible from the northern hemisphere. We couldn't get a look at it here in Northern Ireland. And some comets are like that. So you may be unlucky. You may have to wait 20 years. In fact, you may have to wait even longer. If you look at the top, near the top of this list, we had two bright comets, even great comets, in 1910. We then had one in 1927, but then had to wait until 1965 for an object that everybody agreed was a great comet. And if there's anybody in the audience that observed Arend Roland in the 1950s, I'll bow to your expertise, but I didn't think it quite made this list because all the comets in this list had magnitudes in twilight or dark skies of at least magnitude 0 or -1. Apart from possibly two of them, the Great Daylight Comet of 1910 and Comet Halley-Bapp in 1965, but they were truly visible by eye during the day. We have a magnitude of -5 for the Great Daylight Comet in 1910 and -10 for Halley-Bapp. So we get one of these tremendous spectacles once every 10 years or so. What makes those comets a great comet? Why do they become great comets? Well, looking at this, effectively, I think it comes down to these four factors: size, composition, orbit, and the position of the Earth. And I'm going to go through these factors in turn and explain why I think these are the important factors. So first of all, size. And when I'm talking about size here, I'm talking about the size of the nucleus. So here's a wonderful slide of all the comets, comet nuclei, these ice and dust balls at the heart of each comet. Here's all the resolved images we have obtained so far from either from Earth or from spacecraft, apart from one example, which I'll point out in a minute. And one can see that they span a range of sizes. In the middle, we have the nucleus of Comet Halley. And Halley's comet nucleus is the largest nucleus we have visited yet, back in 1986 in this wonderful image from Giotto. If you go over to the left of this image, one can see slightly smaller nuclei, roughly half the size or a third of the size, Comet 9P1, which was visited by two spacecraft, Deep Impact and Stardust Next, and also 67P, which of course was orbited by Rosetta. Also in this image, we have comets that have not been visited by spacecraft, but we've been able to measure or at least get an indication of their shape by radar. And that can only happen, however, when the comet comes particularly close to the Earth. And so between Comet Halley in the center and Comet 9P Temple 1 on the left, we can see Comet's 2016 BA14 pan-stars, and that is an image from planetary radar because this comet passed quite close to us. In fact, all of these images are from spacecraft or the Earth. One, however, is from Mars. If you go to the right of Comet Halley and up at about the 2 o'clock position, you see a small fuzzy, barely resolved image of the nucleus of Comet Siding Spring. And this is an image taken by the Mars Reconnaissance Orbiter when that comet passed Mars back in 2013. So, we'll try any way we can to get images of these nuclei. Now, you can see they span a range of sizes going from 15 kilometers long with Comet Halley down to maybe 1 kilometer, even half a kilometer for the smallest comets. And that has a direct bearing on our brightness. Because remember that when we see a comet and we see those tails of a comet with something that we're looking for, the more material there is in the tail, the brighter it will be because there's more of it to reflect sunlight. And to get more material in the tail, we need to eject more from the nucleus. So the larger the nucleus, the brighter the comet generally. We have to be careful about this because on average, less than 10% of the surface of a nucleus is emitting material. The rest of it is covered in this inert crust of dust where gas is only possibly just seeping through it gently. And so most nuclei only emit that material that's going to form the comet that we see with our eyes from particular regions. And again, if we look in the center of this image of Comet Halley, we can see those jets of gas and dust coming from the sunward side there. However, there are now, we understand, a population of objects which we call hyperactive comets, which appear to be active over their entire sunward surface. Either way, the bigger the nucleus, the more material you emit. Now, only out of all of these nuclei, only one of them, as we'll see later, Comet Halley, can have been considered in the past a great comet. But if we look at where the comets lie, if we see a comet that doesn't get too close to the sun, but it still appears very bright in the sky, and it doesn't appear isn't close to the Earth as well, we can infer that the nucleus must be large just to generate the amount of material that we have. And this, I think the best example of this was Comet Bennet, discovered at the end of 1969, but really bright in the sky in 1970. And Comet Bennet didn't get that close to the sun. It didn't get that close to the Earth, and yet it was still 0th magnitude in the sky as seen from Earth. And so we can infer that Comet Bennet had a very large nucleus. Now, apart from the size of the nucleus, the next thing we need to worry about is composition. What the relative amounts of gas and dust that a comet is emitting. And I'll show you what I mean from this figure here that I prepared yesterday. When we look at the light being reflected from a comet, from the atmosphere and from the tails, it's being reflected from the gas molecules, and it's being reflected from the dust particles. But gas and solid dust particles reflect light in different manners. If we look at the dust that's in a coma or a dust tail of a comet, these are solid particles, so they reflect light at all wavelengths. Now, can you see my cursor on this on this slide?
Yes.
Yep, thank you. Okay, that makes things a little easier for me. Thank you. So along the bottom here, I've got wavelength of light, if you like, color of light, going from the ultraviolet through to the start of the visible spectrum, blue, going through the middle of the visible spectrum, green, going through to the very deepest red that we can detect with our eyes, and even then starting to approach the near infrared. And what I've plotted here is I've actually calculated the model of the light that will be reflected from the dust particles in a comet. And what really got here is effectively the spectrum of the sun, but slightly distorted. And one can see that we get lots of light reflected from the dust particles at all colors or all wavelengths of light. Now, the gas that's emitted by the comet scatters or reflects light differently. It only does it at certain wavelengths or certain colors. This is one of the things that is explained by quantum physics, and in fact, trying to calculate how this is related to the amount of the gas involves some of this quite complicated physics. But here we can see these spikes in purple, and this is the light that would be reflected by the gas molecules in the comet. And you can see that there are some wavelengths where there's a lot of light emitted or reflected by the gas molecules. And there's some wavelengths where there's very little light reflected. And to get the total brightness of the comet, we have to add up the light reflected by the dust and the light reflected by the gas. So you end up with this blue line here, which is the two lots of light added together. And one can see that we get light reflected at all wavelengths, but at certain wavelengths, we've got a lot of light from the gas as well as the dust, and in particular towards the green region of the spectrum. Now, this is light due to carbon molecules in the comet. And one can, in fact, this is why with modern digital cameras, when one takes images and pictures of relatively bright comets, one sees this green coloration around the head of the comet. And actually, if I go to this picture here, this is another picture of NEOWISE, and this is one that I took, I think, in mid-July. And if you look very carefully, one can see that the very head of the comet appears greenish on this slide. And that's that light being reflected from the carbon molecules in the head of the comet. And behind this, then we can see the yellowish dust tail reflecting the yellowish light from the sun. One can hardly see blue gas tail here. So that's that's how light reflects from this comet. Why is this important for great comets? It's because if we go back to this diagram, we can see that the amount of light we get depends on the amount of gas and the amount of dust. If, for example, there's a lot of gas in the comet, then we might see a very bright greenish comet. If there's a lot of dust in a comet, one might see a very much different appearance of a comet. But because the dust reflects light at all colors or all wavelengths, you've got much more chance of a great comet coming from a dusty comet. And just to show you this effect, here's my theoretical calculations again. The blue spectrum at the bottom is the one I showed you before, where the gas is pushing out a certain amount of dust particles from the nucleus. And in the black, I've now calculated the amount of light coming from the comet if it pushes out 10 times more dust particles, because there's 10 times more dust particles in the nucleus. And you can see the tremendous jump in brightness from down here to up here in the visible region of the spectrum. And this was the primary cause of one of the best great comets of the last century, Hale-Bapp. Hale-Bapp was a tremendous comet. Can I just say, by the way, that when I was looking at a few things yesterday or the day before, in preparation for this talk, I came across a website which tried to argue that Comet Hale-Bapp wasn't a great comet. I can only assume it was done by somebody who wasn't born in 1997 when Hale-Bapp was around, and you could walk out of your door, your front door, look up at the sky and go, look, there's a comet. So yeah, there's no doubt that Comet Hale-Bapp was a great comet, and many, many images that you'll be able to find on the web, and maybe you even took yourself. One can see the curving arch of the dust tail and this lovely blue gas tail or ionized carbon monoxide tail. But the important thing is that Hale-Bapp was a really dusty comet. It had relatively about 10 times more dust relative to gas than a normal comet. And so it reflected 10 times more sunlight effectively. And that's what helped it become so spectacular in the night sky. Excuse me, my coffee's getting cold. Right, so we've got size, and clearly the composition helps to create a great comet. The next thing, and one of the most important, possibly even certainly more important than compositions most of the time, is orbit. Now I'll put up a complicated diagram here, but what this diagram shows is along the bottom, the distance of a comet from the sun, and it goes logarithmically. So you start perhaps at half the distance from the Earth to the sun here, to 1 astronomical unit, the distance between the Earth and the sun, to 2, to 4, to 8, to 16. What I've plotted here are is the amount of molecules that would be released per second per square meter of surface for different ices, whether it's nitrogen ice, methane ice, carbon dioxide, ammonia, or water. And one can see, for example, an effect of why we don't see very bright comets out in the outer solar system. They're mostly made of water, but water really only gets going. It only starts being released in great quantities once you get within 4 astronomical units of the sun. But the important thing is that once you're in this region, once you get within the asteroid belt and certainly within the orbit of Mars, your rate at which you release the water and the other gases and the dust just keeps going up. And just as this is a logarithmic scale, this is a logarithmic scale. So if I go from this number 20 here to this number 25 here, that doesn't mean you're going from 20 molecules released per second to 25 molecules released per second. That's 10 to the power 20 to 10 to the power 25. So you're increasing as you go from here to here, the rate at which material is leaving the comet by a factor of 100,000. And so the closer a comet comes to the sun, the more material it will release, the brighter it will be. And there's been some great comets that have become great comets because of that. An example, and one which unfortunately I didn't see, was Comet West. Comet West was a beautiful comet in the mid-1970s, and as I said, unfortunately, my interest in astronomy hadn't quite been peaked yet, so I missed it. Here's a wonderful image showing how it appeared in the twilight sky from Alan Hale. This is a much more famous image, a slightly longer exposure by J. Linder at the European Southern Observatory, And one can see this was a beautiful, beautiful comet, Comet West. And one of my joys of my career is actually working with Richard West, its discoverer, when we did our Hale-Bapp campaign 2 decades later in 1997. But Comet West came within, I think it was about 0.15 astronomical units of the Sun. Much closer still was Comet Ikea-Secchi 10 years earlier in 1965. This was a type of comet we call a sun grazer, which approaches within only 1 or 2 solar radii of the solar surface. And in fact, this is a wonderful image from a chronograph, a telescope designed to study the inner corona of the Sun, just above the solar surface as seen from Earth. And this was taken just at about the time, within an hour or so, of Ikea-Secchi being closest to the Sun. And one can see that this comet is really just moving around the Sun incredibly quickly at this point as it rounds the Sun to come back out again. And when it came back out again, it was a glorious sight in the evening sky. I apologize, by the way, I think this is the only image I have in my slides where I don't have a credit to it, because I couldn't find the definite credit for the person who took this. I need to look this up a little bit more. But in 1965, Ikea-Secchi was a truly great comet, as one can see here, with the tail stretching through Bootes, the herdsman, if you can recognize that pattern in the evening sky, and truly a tail spanning tens of degrees. Now, Ikea-Secchi was a beautiful comet, and another sun grazer we have had recently, much more recently, was Comet McNaught in 2006. This was a truly spectacular comet. Unfortunately, again, like Comet Lovejoy 5 years later in 2011, not that visible from the Northern Hemisphere. But it was truly spectacular in the Southern Hemisphere. And in fact, some of my favorite images were taken from the European Southern Observatory at Paranal. And here we can see the comet after sunset with its tremendous, highly structured dust tail stretching over 3 of the units that help form the Very Large Telescope Interferometer. This was a great comet because it could certainly be seen in the evening sky by eye. You would just go out and look at it and see this tail spanning tens of degrees. It was a daylight comet as well. This is a beautiful image of the comet just rounding the Sun. I think this is about 7 hours after it went around the Sun, taken by Stefan Siep in Germany. It was several degrees from the Sun. It didn't get that close, not as close as Ikea-Secchi, but it really was a spectacular sight. I remember that was my only chance of trying to see it at Christmas time 2006, and unfortunately I never saw it, but I'd love to hear if anybody here did see it in the daytime. As I said, however, it wasn't really that visible from Earth, from the Northern Hemisphere, as was the case for the last great comet we had at the beginning of the 2010s, or rather 2011, Lovejoy, which again was a beautiful comet in the twilight sky. But clearly then, the important thing for us on Earth to get a great comet is to have it get near the Sun. But there's one other important factor that can make a comet truly great. Its location, location, location. It's how close is it to the Earth? And let me explain by a little diagram. Here we've got a comet coming in on its orbit and going around the Sun. The orbit of the comet is in black, and I've put where the comet is here. and in blue we have the orbit of the Earth. Now, how we see that comet, how bright it is and how large that toe appears in our sky depends on where the Earth is relative to the comet. If the Earth is here, it's frankly a bit rubbish. It's on the other side of the sun. We can't even see it in the nighttime sky, and it's 2 astronomical units away or more. If the Earth is here, it might be nice. This looks like it's going to be a nice, well, I've got to get my angles right here. It looks like it's going to be a nice comet in the morning sky. We're going to be about 1 AU, and 1 astronomical unit from the Earth, about 1 astronomical unit from the sun. If it's got a big nucleus and it's ejecting a lot of material, then hopefully it'll be relatively bright. It might be a nice comet. If the Earth is at this point in its orbit, it's going to be great. It should be pretty bright as seen from Earth. But wouldn't it be great if we were there? Oh my gosh, that would be absolutely tremendous. And as intimated by Paul, the first comet I ever saw was of this nature, Comet IRAS-Arakl-Alcock, back in 1983, where I remember I was a first-year undergraduate student over in my university, and literally walking from the halls of residence to the student bar, you could look up and you saw the comet. An hour or two later coming out, I looked up, the comet had moved. It actually had moved. It wasn't because it had a pint of cider or anything like that. It really had moved. And this is just a lovely image I found on the web by Joanne Plusiennik. I'm not sure how to pronounce the name, I do apologize. But one can see over the motion of the comet over 30 minutes. This was not a great comet. It's actually a relatively small and very relatively inherently faint comet, but it passed very close to us. One could see it move from hour to hour across the night sky. If one has to think of a comet that became a great comet because it was close to us, then the obvious example was Comet Hyakutake in 1996. And I'll still remember the night I went out with my friends to Crawfordsburn between Belfast and Bangor for a good dark sky around about 11 o'clock or midnight that evening. And the comet was like a searchlight with the head of the comet near Polaris. And so it's circumpolar as seen from Northern Ireland. It didn't set. And you could literally just look up and see it there. It was absolutely astounding. And it'd be lovely to see another one like that in the Northern Hemisphere. Now, we will do again, because the vast majority of comets, the great comets that I've shown you up to now, and the vast majority of great comets that we've actually ever seen in our skies have been effectively one-time visitors. There have been long period comets with orbital periods in the ranges of thousands of years to tens of thousands or even hundreds of thousands of years. But there's one regular visitor to our solar system that can on occasion be a great comet. And it's the first. It's Comet Halley. This is an image that many people, I'm sure, will be familiar with. In 1066, it appeared in the night skies. It was a relatively bright apparition. It was relatively close to the Earth. And one can see on the left, people looking in wonder at the comet in the sky, and a servant coming to Harold and saying, King Harold, perhaps you don't want to do this battle because the omens aren't too good. And if you ever go to Bayeux and actually see the tapestry, it is a beautiful, beautiful comet that one can see there. Now, in 1910, Halley had an amazing passage to us. It really was a truly excellent apparition. And there were two bright comets that year. There was the Great Daylight Comet, which appeared a few months earlier in the sky. Halley was slightly fainter, but it was still a very impressive comet. It reached first magnitude, and the papers were full of it. It was basically it was pre-Twitter days, and people still made a fuss about it. So on the left, we have a report from the New York Times about the discovery of cyanogen in the comet. Of course, this spectroscopy was still in its early days at those stages, but they found cyanogen in the comet. It was bright enough, and so they could tell what it was made of. And this caused a panic because it was predicted that the Earth would pass through the tail of Comet Halley, which it did. So on the right, of course, you have anybody trying to make a quick buck, and we have Hope's anti-comet pills. Although I must admit, I'm not intrigued by this. I'm actually intrigued by the remainder of the New York Times article, because I'd love to find out what happened to the Archbishop's carriage down here and how they managed to rescue the horses from their blazing stable. But it was a true sensation, just as Hale-Bapp was in 1997. I love this. Comet parties now are the fad of Paris. Now, thank gosh, they weren't trying to do it today in our lockdown times. But of course, we can see how men were asked to wear pale blue evening dress and ladies to don gowns the colour of the firmament. And of course, if you're going to one of these comet parties, you can drink your comet whiskey down there on the left, or maybe you've got simpler tastes like me, you just like a bottle of comet ale in a bottle. And of course, one must remember in 1986, we did indeed have Halley's Comet wine that was brewed. Unfortunately, it was distilled or created by a winery in England. And unfortunately, it wasn't that great, but neither was the apparition. Let's be honest about it. Comet Halley only reached third magnitude in 1986. This is a shot of it from the southern hemisphere. And if it's any consolation, the next visit in the year 2062 will be even worse. So if you saw it in 1986, great. If you didn't see it then, don't worry, you didn't miss that much apart from seeing a famous comet. There have been better comets since then, and there will be better comets in the future. Which leads me on to my last couple of slides. So when's the next great comet coming? Well, we don't know. We don't have one on the books yet. But here's a plot that I've updated since I gave it last year at the BAA meeting in August. I think it was in the summer last year in Armagh. And what I've done is I've plotted the number of comets discovered each year from 1990 all the way up to so far this year. This is up to October this year. And what you can see generally is that the number of comets being discovered is generally rising from year to year. Now, this is mostly because of the big telescopic surveys we have now that are hunting near-Earth asteroids. They also pick up anything else that moves out there, including new comets. And most of these new discoveries are distant comets. But that means that the next time a great comet is approaching the solar system, we may not be taken by surprise. We hopefully will have some time to plan. In fact, if we look here, if we look over the past 20 years, we can see how distant these comets were from the sun when they were first discovered. So I've got data along the year along the bottom here versus the distance from the sun. And one can see that even in the last decade, in the 2000s, we were mostly finding comets, of course, close to the sun, but there were a few that were outside the orbit of Jupiter. As we go to, well, I suppose that was the second last decade. If we go to the 2010s, we are regularly now finding comets a long way out, years before they approach the sun. And that means when we find the next great comet, we'll all have time to get onto Amazon and buy those new, and will be justified in buying those new telescopes, new cameras to our partners and our loved ones, because we know we've got an excuse. So I'll just finish with this slide, the slide I've shown before. What is a great comet? It's a comet as bright as the brightest stars. It's a comet with a visually long tail, at least 10 or 15 degrees long. It should be seen in a twilight or dark sky. We've seen them over the past few decades. They will come again. You've just got to be patient. Thank you for your attention, and I do apologize for the technical difficulties at the start.
Well, Alan, thank you very much for that. That's absolutely fascinating. I remember a few of those myself. I did see Halley's Comet in 1986 through my father's binoculars. As you say, it wasn't terribly spectacular, but at least I've seen it, and I won't, medical miracles aside, probably get another chance. So, and the next one won't be great either. But one that you didn't mention, which I thoroughly enjoyed myself, because it was very, very unusual, was, I think it was 2009 Comet Holmes. That was
yes,
wasn't it?
Yes, well, 2008, I guess. Yes, for those of you who may not remember or are not aware of it, Comet Holmes is a short period comet. It's 17P Holmes. It was the 17th comet with its orbit calculated. And in 2008, it underwent a massive outburst, a massive eruption. One night, it was 15th magnitude. And the following night, it was 3rd magnitude. Just by ejecting a huge amount of material from its surface. And in fact, it turns out it has done this at least once before, because it was originally discovered in 1890 something. Oh, can we mute people, please? So
yes,
can you
turn your mic off if you're not talking, please.
Thank you. Thank you. Sorry about that. Anyway, yeah, that was really impressive. And over the following nights, you could see this material expand outwards because it wasn't being continuously generated. It was generated in the first few hours of that outburst, and then it just gradually died away. Although the comet was more active afterwards. I didn't put it here because, first of all, it didn't reach 0 for 1st magnitude. It kind of maybe reached 2nd magnitude. And it didn't have a tail. Sorry, it just didn't have a tail. It was really impressive to see. Just like NEOWISE was, right? In the early morning, through the noctilucent cloud. I know a few people saw that, as I did, by just hanging out the bedroom window in early July. But it wasn't in a dark sky. Holmes was in a dark sky, but it wasn't. It didn't have a really spectacular tail. Lovejoy had a nice little tail, but it wasn't in a really dark sky. You couldn't really see it that easily. It was kind of a bit fuzzy, you know, it had a little bit of a tail. So I think you've got to be honest with yourself. I mean, as I pointed out, all comets are great.
Yes.
Yep. All comets are great.
Fascinating objects.
But we have to keep ourselves reined in a little bit and save this name for the truly magnificent objects that we see when they come to visit the inner solar system.
Okay, just a couple of things in the chat that I'll sort of bring up as we went on.
Yes, I can't see the chat. Sorry about this.
Now, David Moore from Astronomy IE is with us this evening, and he saw Comet McNaught in daylight from Dublin several times, he mentions here.
Brilliant, brilliant, excellent.
That's good.
Excellent, that's fantastic.
An interesting one actually from Paul Campbell. Galway Astronomy Club wrote that it was the interest actually in Comet Hale-Bapp in 1997, which I myself saw from Wimbledon Common in London, where I lived at the time.
Yeah.
And that sowed the seeds of the Galway Astronomy Club, which is still
fantastic.
So that's brilliant.
So I've actually spoken to Galway Astronomy Society before, and a couple of times, and very much enjoyed it. Thank you. If Hale-Bapp isn't in the emblem for the Galway Astronomy Society, why not?
Why not? What a great question.
My response to that.
Paul, you mentioned it. Paul Campbell, you mentioned that. Do you know if that's the case or not?
I'm not sure. I just was aware that the club was formed in 1997, and it was to do with the Hale-Bapp, you know. So I just thought I'd mention it.
Fabulous.
That's really good.
Brilliant. Terry, you've mentioned two other comets there. Do you want to mention those, Hale-Bapp and Hyakutake?
Yeah, Alan, thanks for a superb talk as always. Your slide of the size of the nuclei of the various comets didn't include Hale-Bapp. Now, obviously, it was so far away that we couldn't measure it directly, but as an estimated size, would it have been about double the size of Comet Halley?
More. You're absolutely right. Yes, I'll brought up this slide again if you can see it. This is a slide showing just comets where we have resolved the comet, i.e. we can put a ruler, if you like, on the picture and measure the size. We couldn't do that with Hale-Bapp because its closest, it was about, I think it was about 1 astronomical unit away. But we have indirect measurements of it, and the general consensus is the nucleus of Hale-Bapp was 70 kilometers across.
Wow.
Yeah, it was a big one. To be honest, I could have put Hale-Bapp in the size category as well as the composition category, but it's clear that Hale-Bapp was also very bright because it released just so much dust that could reflect so much sunlight. So I thought I'd spread them out a bit. But yeah, Hale-Bapp is actually the largest nucleus for which we have a confirmed, nucleus I should say in the inner solar system, for which we have a confirmed or reliable size estimate.
Right, thanks. And the other one, which I think was even brighter and better, maybe not brighter, possibly, briefly, was Hyakutake. And it was absolutely amazing. I know Hale-Bapp was around for ages, whereas Hyakutake whizzed past. But the Coma was an electric blue, and it was the size of the Tyrone. And as you say, I saw it actually in the dark skies of Tyrone. And the tail literally went not the whole way across the sky, but almost halfway across the sky.
Yes.
And to me, I've seen Hale-Bapp was good. You could see it over a number of weeks, months even. But Hyakutake at its best, to me, was the better of the two comets.
Well, yeah, I feel good to try to pick between them. What I'd point out again, this is this composition though rearing its ugly head again. As you say, it's electric blue, this bluey green, because there's very little dust being released by the nucleus at that stage. It actually didn't develop. Something happened to the nucleus after it passed the orbit of the Earth, and it started producing more dust afterwards. And in fact, about a month later, I remember seeing it in the evening sky. You could clearly see the dust tail quite easily, but the gas tail had gone. But at that time, when it passed over us, and I think all of us who saw it have those amazing memories. What you were seeing, that tail was the iron tail or the gas tail of the comet, and it is pretty rare for a great comet to have a tail really dominated by the gas, and Hyakutake was it because it was so close to us and we could see that gas so clearly.
Brilliant.
Yeah, I couldn't see the colour in the tail itself because it was below the visibility for colour, but the head itself was just mind-blowing. Anyway, thanks very much, Alan. I'll leave it there.
Brilliant. Okay, we've got a bit of information coming from John Flannery. Many thanks, Alan. Terrific overview. That's John Flannery in Dublin. And Halley is in the logo of Limerick Astronomy Club, as it happens.
Ah, excellent.
So they got there first. From Jerry Davidson, comets contributed to the water in our oceans and seas on the early Earth. What percentage of water would be from comets, do you think, Alan?
Well, here lies a debate. Here lies another talk. We don't know. One of our problems at the moment is that we now have good measurements of the water and the different types of water in about 6 comets from the Kuiper belt. One of the original reasons for the Rosetta mission to Comet 67P was that it would it would measure this water and show that comets from the Kuiper belt, like 67P, had delivered water to the Earth. In fact, it showed that a comet like 67P couldn't have delivered the water to Earth because the ratio of heavy water, where water's got an extra neutron in it, compared to the normal water, was just all wrong. It doesn't match the water on Earth. But we now have measurements of 2 comets which do match it. So at the moment, it's a confusing situation. We don't know. We certainly know that the comets and icy bodies from the outer solar system must have and did hit the Earth and deliver water to Earth in the early years. But we don't know now how much of that water that we have on Earth today was delivered by comets. And this is really a hot topic of debate, and has been since Rosetta returned its first accurate measurements in 2014. I think the debate's going to continue for quite a few years yet.
Brilliant. Okay. Now, Caroline and Hayden are with us, and they have their hand up. Caroline, would you talk?
Hi, Alan.
Hi, Caroline.
How are you? This is a question from Hayden. Of course, we obviously have to get the planetary defence perspective thrown at you. It's just the other day we joined in the conference about Sentinel-6. They were talking about climate change, sea rising. Now, Luca Parmitano answered Hayden's question that he noticed the significant changes within his 2 space flights. 2 space flights has passed 6 years. Mm-hmm. But during the conference, Hayden picked up there was no mention of planetary defence whatsoever. Mm-hmm. How important should planetary defence be working with Earth observation and the catastrophic impact of an asteroid or comet, with especially with the sea levels already rising? Thank you.
Yeah. Well, the important thing, of course, is that Hayden's absolutely right. Planetary defence is really, really important. Now, if a comet hit us, we wouldn't have to worry about the extra water coming from the comet making the sea rise a little bit more, because in fact we'd have a whole lot of other stuff happening, as Hayden well knows, in terms of the impact effects with the cratering and the fireball and the dust in the atmosphere and so on. At the moment, if we look at comets, the risk from comets is actually quite small compared to the risk from asteroids. And that's why in planetary defense, we concentrate on finding the asteroids. Although, as I've mentioned previously, we actually find everything that moves within the field of view of the telescope, or we try to, let's put it that way. So the same telescopes that are looking for asteroids are also looking for comets. And in fact, on the Atlas project, which I spend quite a bit of time working on at the moment, we found about 50, 60 comets so far over the past 2 or 3 years, which is really nice. But the interesting thing is that in planetary defense, we're making a catalogue of all the asteroids that we can find. And it's going to take a long time. It's going to take years and years and years. But eventually, that catalogue will be near complete. And every time we find another asteroid, calculate where it's going and put it in the catalogue, we've checked that it's not going to hit the Earth. So once that catalogue is near completion, once we've got the book of asteroids nearly done, at that point, we're going to be finding out, we believe, that we've now got to really starting to think about the comets again, because comets are on orbits that can take hundreds or thousands or tens of thousands of years. There are comets out there now, many of them heading in towards us, that we don't know about. So at some point, we'll have found all the asteroids that we need to some point in the future. And at that point, we're going to have to switch to really concentrating on finding these comets.
Okay.
Brilliant, Alan. Thank you. It was just a perspective, for education and outreach. It's just something that we feel that we should bring in, especially in the learning with the Earth observation combining with planetary defense. But thank you very much for answering the question.
That's okay.
Okay, next up on the chat, we've got John Fagan just reports that his first comet was Hale-Bapp, and he's now seen 6 and hoping for another one, NEOWISE being the last there. Now, how's this for a story then? Ken, reports that his grandmother saw Halley's Comet as a teenager in 1910, and he took her out to see the 1986 occurrence at the age of 89. Wasn't quite convinced that she actually saw it, but was delighted to receive a certificate from our Observatory for having seen it twice.
Whoa! That's
isn't it?
Frame that certificate. That's impressive. As I said, I'll be 98 when Halley comes around again. I'm not convinced I'm going to make it either myself. So that's brilliant.
Yeah, it is terrific, isn't it? Now David Moore in Astronomy IE says, Atlas must have imaged NEOWISE loads of times. Did anyone collect the images and make a gallery?
The answer is no and no. Atlas didn't image NEOWISE lots of times because, like all telescopes on the surface of the Earth, we can't get too close to the sun. And so we did image it a few times with Atlas, and it looked nice. It was a bit bright, brighter than what we normally expect, so it's completely saturated on the images. But the important thing is that if you want nice images, I'd stick with the amateurs. The tremendous images being given by being obtained by the amateurs are much prettier than the images, I'm afraid, that we got on Atlas. So I'd stick with those.
Okay. Frank Butler says, thanks, Alan. Really enjoyed the talk. Terry, you had an answer to the question about heavy water and Bennu.
Yeah, well, hopefully we get the sample back from Bennu, which seems to be a lot more than their target amount. I'm just wondering, do you think there'll be enough water in that sample to be able to determine the ratio of heavy water in an object like that?
Yep. Remember that OSIRIS-REx is not the only sample returned to a primitive asteroid. High-Rising 2 has already left Ryugu, and it will be back at the end of the year. It's on the fast trajectory. So within the next 3 years or so, we're going to have 2 samples back, and indeed, they're measuring the water content and the isotopes, or the deuterium ratio, the ratio of heavy water to normal water in those samples will be one of the first things they do, along with all the other isotopic measurements that they'll be able to do in the laboratories on Earth. So absolutely, there won't be any problem.
Thanks.
Okay, Andy McRae, you had a question. Andy? Okay, what Andy was asking about, he said, thanks for a great talk. What happened to QUB?
Yeah, what happened to QUB? So those of us who are of a certain age might remember back in '73, I think it was, that the papers said, oh, there's going to be the comet of the century coming. And it didn't. It was a reasonable comet, Comet QUB. I think it reached 6 magnitude that year. So not bad. So pretty good these days for everybody with modern equipment. But this was one of those stories which got hyped out of proportion, where it was detected quite a way out, and somebody did a few calculations, said, oh, it could be this bright coming in, and unfortunately wasn't. One always has to be careful with predictions of cometary brightness, even with Hale-Bapp. Hale-Bapp was discovered 2 years before it reached perihelion, before it got close to the sun, and everybody was nervous, particularly partly because of QUB and the poor prediction that it was going to get very bright and almost be a great comet, and in the end it wasn't. So we were desperately hoping that Hale-Bapp would last the 2 years coming into perihelion, and it did. And in fact, I can see on the video, I can see somebody holding up. Who's that?
Ron Hills.
Ah, hey, now that's a lovely image. Is that Hale-Bapp?
That's Hale-Bapp, signed on the bottom by Thomas Bapp himself on the 20th of June, 20th of June '97. He gave a talk at Armagh, and he signed this for me.
Wonderful. Yes, yes. They certainly, well, and deservedly did the rounds on the back of their discovery. But what a great discovery it was, and it was wonderful to actually meet them during that period. So I think Thomas has now passed away, unfortunately, I believe. But I think Alan is still with us. So. So it's still nice, but that's a lovely memento. Yes, keep that one framed as well. That's lovely. That's lovely to see. Thank you.
I think that it has changed its color a bit over the years. It's a little too red.
We all change color over the years. I wouldn't be worried.
Very good. John Flannery just points out he's got a Sky and Telescope magazine from the year of Hyakutake, which has a full-page ad for people to travel on the QE2 to see the comet. That's well, you're guaranteed a dark sky that way, aren't you?
Only if the captain turns the lights out.
Yes, of course. Yes, yes. Well, that's all the end of the chat. Is there anybody else wanted to ask any questions of Alan before we just throw it open for general chat?
So I just spotted there was one from Andy McCrae. But he said, he asked what happened to Hyakutake, but is there theoretical maximum size for a comet nucleus? Not theoretical, but an effective size, kind of maximum size. Pluto. Pluto's a big ball of ice. Bring Pluto into 1 AU from the sun, you'd have a comet and a half, I can tell you. Yeah. So not really, no. And in fact, it's a good question. It's down to a matter of semantics then. However, we do believe that all of these comets formed in the early solar system. And so the question about the maximum size of a comet is that is there will be some kind of maximum size based on when the accretion, the coming together of all those ices and dust particles finally slows down and stops because you run out of material to accrete onto them. But there are probably comet nuclei out there, or we know there are comet nuclei out there which are several hundred kilometers across, because you take anything from the Kuiper belt, any of the large Kuiper belt objects that we have orbiting beyond Neptune, which is where the short period comets come from, and bring them into the inner solar system, and you're going to have a comet and a half, I can tell you. I'm not sure what you'd have beyond Great Comet. Stupendous, amazing, magnificent. It's leave that as an exercise.
They could follow the traditions of the telescopes, couldn't they?
Well, super. I couldn't find my own. Sorry, can you hear me, Alan?
Yes.
Sorry, mate. Listen, I just said to Paul as well, your talk was a great talk, but like comets, all your talks are great talks. So, it really was good, despite the technical hitches. Just one other comment. Comets, there was a thought that comets came in sort of clusters, almost ones and twos. I mean, these bigger, brighter comets. Is there any strength in that? You think about the 1910 and
the answer to that is...
Think about Hyakutake, Hale-Bapp, when you think about I have a great print.
Yeah, so the answer to that is no, because their orbits around the sun are completely different. There's no way they can be related. However, if you go to, say, the Jet Propulsion Laboratory, and you download their catalogue of 3,500 comet orbits, you will find that about 2,000 of them, or maybe 2,500 of them, are extremely similar. And that's because these are all the SOHO comets that have been found by solar observatories, particularly the SOHO satellite, over the past 20 years or so. Now, why do all these comets coming into the sun, they're all sun glazer comets, by the way. Why do they all have the same orbit? It's because at some point in the unknown past, probably at least several thousand years ago, there was a giant comet that went around the sun, split apart, and right now we're seeing all the individual bits coming back. We don't know when this great progenitor did round the sun and split, because the orbits of the solar comets are so poorly known. We see them come in, we don't see them go out because they all vaporize. They pass just above the solar photosphere and get vaporized. So we can't calculate the orbits properly, which means that we don't know the orbital period. But all we know is that at some point, probably a few thousand years ago, there was a truly great comet rounding the sun, which would have been an amazing sight as seen by the people living on Earth then. That would have been quite scary.
Alan, sorry, could I just come in on that? Because that's actually a question I was going to ask related to that. If it was that great and bright, would there not be a record in the ancient Chinese observations? Let's go back to about roughly, what, 1500 BCE for comets?
Yeah, no, it would be further back than that.
Right.
We're possibly talking 8,000, 10,000 years ago.
Right, I thought you said a few thousand. Right, okay.
Yeah, well, look, we're guessing. All we know is that the people have, to be honest, historians of science have worked with cometary astronomers in the past to try to identify it. And I think there was a Babylonian tablet from about 3000 BC, which they thought could be it, but it wasn't very convincing. And then you were too far back, unfortunately.
Right, thanks.
Sorry, Terry, I think I recall reading about 2 of the nuclei being seen around Roman times.
Of the Kreutz family?
From the Kreutz family. So I might just have to go back and check my references where I found it. But I do recall coming across potential references from Roman times.
So they would have been bigger fragments, not the little ones that Soho sees.
Yes, yeah. Because of course, besides the Kreutz, you have the Mac, and there's a few families besides the Kreutz comet group. So, like whether they're all the same progenitor, I'm not sure.
No, they can't be the same progenitor again. There are at least 3 families of sun-grazing or near sun-grazing comets, but they all have different orbits about the sun. So they all come from different progenitors. But the largest family is the Kreutz family. A bit of Kreutz comet gets vaporized about once every 1.5 to 2 days. At the moment.
Yeah, when you see the tally on spaceweather.com, like it's extraordinary how many sun grazers are there.
I was just thinking, 8,000 years ago, would that not be the end of the Ice Age? But there might be a lot of people not around in the northern and southern hemispheres to witness that if it was the Ice Age.
I'm afraid my my knowledge of history back then is worse than 0, so I couldn't comment on that.
I think the Ice Age.
Well, it would have been 10,000 years ago. Yeah. It would have been coming down to the end.
Yeah. But honestly, we really don't know when that progenitor was around. It could have been 5,000 years ago. It could have been 8,000. It could have been 10,000 or 12,000 years ago. It could have been even longer. Our problem is that we don't know because we don't know the orbital period of the Kreutz family comets that we see coming in and getting vaporized. So, but I'm sure one day we will. The problem is that we needed somebody to have invented writing or at least drawing pictures back then to leave us a record of it as well.
Alan, are any of the solar probes capable of detecting these incoming Kreutz family minor ones accurately enough to get an orbit for them and then give you some indication about the parent body?
Yeah, there's been people been looking at that, and particularly with both the Parker Solar Probe, there's some possibility for detecting the Kreutz family comets, and also with Solar Orbiter. And you're absolutely right, Terry. The advantage they'll have is that actually their positional accuracy isn't that great. They tend to have large pixels in their cameras, but that that disadvantage is overcome by the advantage that they're in a different place in the solar system. So you get a triangulation if you can detect one of these fragments from the ground and from the Parker probe or from solar orbiter. So you can immediately get a very accurate measurement of the orbit, funnily enough, because you've got that three-dimensional triangulation. But I don't know the status of that. It was certainly proposed by Carl Battens and others over in the States for the Parker Solar Probe, and I don't know the status of that program though.
Okay, thanks. That's really interesting.
Okay, Alan, we've got one just come in from a question from John Fagan, who is relaying this on behalf of Martin McKenna, who is watching on YouTube, so can't ask himself. Hi, Alan. Can you explain about synchronic bands? I've never
right, let's try and find a picture of synchronic bands. There you go.
Perfect.
Okay. What happens when a comet, first of all, what happens when a comet ejects material, particularly dust, is that it doesn't do it continuously. If you remember, I said that the material mostly comes off certain selected areas on a comet, and as the nucleus rotates, that goes into sunlight and then into darkness once per rotation of the nucleus. And so, if you like, the jet switches on and switches off, and so you can get if you like, a kind of bursts of dust being ejected from the comet, which you end up then forming the dust tail. And these, first of all, these synchronic bands that you can see here in this image, or can you still see this image, by the way? I just better check.
Yes.
Okay, thank you. What you're really seeing here is at least partially reflection of the spin of the nucleus and the jets, the material is being switched on and switched off as it's ejected from the nucleus. But it's more complicated than that. In particular, if you look fairly carefully at this, you can see that there are these kind of fairly well-defined streaks, but sometimes they're at an angle, and sometimes they seem to be crossing over, particularly as you go to certain directions, like here, and there's the kind of a curve there and curve there. Understanding that actual structure is extremely difficult, and that's been something that was looked at by Geraint Jones over at UCL and Mallard Space Science Laboratory in London. And what they found was that there may be a combination of factors being at play here. First of all, you've still got this switching on and switching off, this pulsation of material being thrown out every so often into space from the nucleus to be blown back and form the dust tail, the tail of dust particles. But then he suspects there's electrostatic forces taking place as well. And these dust particles are being affected by the magnetic field in the solar wind. And that can give you this kind of cross-hatching that you can see in some of these here. So, so it looks like it's a much more complicated process than one might first thought. But there have been several comets over history, several great comets even in history, which have shown this effect. And so we know it's visible quite often when you have a nice bright dust tail. And hell, let's hope the next one shows these as well.
That's great. Thanks, Alan.
In that illustration, was that comet moving very fast?
The comet itself is moving with the orbital velocity. So what happens is that, if I can explain this, I hope I can explain this clearly. The comet itself is moving fast around the sun in its orbit. Mm-hmm. But what's important here is then when the dust grains are ejected, those dust grains are then in their own orbit about the sun. And initially it'll be pretty similar, but they are constantly being pushed back from the sun by the pressure of sunlight. And so they eventually end up on these curved trajectories relative to the nucleus because they're being pushed, continuously being pushed away from the sun by the sunlight reflecting off the grains. And so you've got a combination of those two effects. The grains are trying to stay in orbit around the sun, but they're also being pushed away. So you get this kind of lovely, you end up getting this lovely curved tail in the dust. And it's lovely.
Thanks. Lovely talk.
And again, just on that photo of McNaught there, and I have a signed copy of a photo that he took himself from the comet over the Warrumbungles in an A1 size, which is absolutely magnificent. What I'm wondering about is over what period of time would those various bands have been produced? And the reason I'm asking that is I try to make sense of the curvature of the basically the inner part of the bands and trying to work out how much the motion of the Earth contributed to that curve. Have you any idea on that?
None of that. Well, the vantage point of the Earth at any point will change the perspective clearly on that tail. But that curvature of that tail is purely due to the orbital motion of the comet and the dust grains trajectories relative to the comet. It's really got nothing to do with the Earth. And in fact, this is a Comet McNaught in this image was a lovely example because we're almost looking face on to the comet in its orbital plane. So we're seeing the trajectories of the dust, of those dust grains being laid out before us, if you like, as if they were laid out on a table. It's actually almost a perfect example of how to put a comet somewhere in the solar system so you can study what's happening to the dust. I can't remember, to be honest, Terry, on the timescale for the ejection of those dust grains. It would at least been weeks,
right?
Maybe longer. I could dig out the paper and send it to you if you like.
Right. Okay. I'm just trying to imagine where the sun is relative to the comet in that photograph. Obviously, just
that's easy.
Horizon. Yeah, I know.
That's easy. Yeah,
it's easy.
The toe points away from the.
I know, but they're all pointing in different directions. That's the whole point.
Look at the head of the comet.
Yes, I know.
That's the material that hasn't had much time.
Yeah,
hasn't spent much time traveling away from the comet. So that if you look at the head of the comet, that will always give you the anti-sun direction too, within a few degrees anyway.
Yeah, and that's why I was trying to tie that in to the curve of the inner part of the dust grains that are given off, and the direction that they're pointing from the beginning to the end.
If you like, I'll give you another pointer. Here's the crescent moon.
Yeah.
Yeah, so you can see the overexposed crescent of the crescent moon just after sunset.
And that points obviously to the sun.
The sun's down here somewhere.
Yeah. I didn't see that actually overexposed crescent. That's neat. Excellent. Thank you.
Very good. Right, one more question on the chat, Alan, here. Why do comets with periods of thousands of years not go far enough to escape their solar orbits? Are they traveling slower than, say, the Voyager probes?
Yes. For that point of the orbit, the important thing is that one has to be slightly careful about this, is that certainly if a comet has an orbital period of thousands of years, then yes, it's in a bound orbit about the sun. It's traveling fast, but not fast enough to escape the gravitational pull of the sun, and so we will always come back, although that orbit can change slightly. What happens, however, is that when we look at the very longest period comets, and we're not talking about Hale-Bapp, we can talk, for example, about Hyakutake, which when they're coming in have orbital periods of hundreds of thousands of years, for example. Then if you do the calculations, you can see that just a very small nudge, if you could just accelerate the comet a little bit by a meter per second, which sounds fast. I don't think I could run a meter per second these days. I've been locked in too long. But the orbital velocities of course, the comets, particularly when they're near the sun, are many tens of kilometers per second. But at that point, if you nudge them by just a meter per second or so, you have a dramatic effect on the orbit of that comet. And it will either end up with a much shorter orbital period, or it will escape the sun completely. It's on a knife edge when they fall in from the Oort cloud. And in fact, roughly half the comets we see coming in from the Oort cloud will never escape. Well, sorry, never escape, will never return. And that's because on their way through the solar system, either they've got a little bit of a nudge from Jupiter or Saturn on the way in, a little bit of gravitational tug, or they've actually thrown out so much material from the sunlit surfaces that they've actually changed their own orbit, because the material goes one way, the nucleus goes the other way, because of the principle of conservation of momentum. And that can also mean a comet will never come back. It escapes the solar system. So if you've got an orbit of 1,000 years or so, generally those objects are trapped. But if we go to the extremely long periods of hundreds of thousands of years, then many of those comets will never return. They've come into the sun once and they'll never be back. They've now been ejected out into interstellar space.
Brilliant. Okay, well, I think we've come to the end of the questions in the chat at the minute. Does anyone else have a quick last question for Alan?
Oh, not my coffee's cold.
Well, and Alan's coffee is cold. Okay, well, look, at that point, so that's an absolutely fantastic talk, Alan. Thank you very much for giving that.
Here, brilliant.
And we're back. Terry, do you want to tell us, because you organise these things? We're back in 2 weeks, aren't we?
2 weeks' time. We have Dr. Yorick Vink from Armagh Observatory and Planetarium talking about 30 years of the Hubble Space Telescope, called Opening the Treasure Chest, which I think will be looking at the most fantastic images that we've got from Hubble. So hope to see you all back in 2 weeks' time.
Okay, brilliant. And right, so thank you very much, Alan. Should we thank Alan in the normal way? That's as
Thank
best
you.
we can.